February 2021, a team of climate scientists at the Potsdam Institute for Climate Impact Research in Germany is running the numbers on something that has been quietly accumulating in the oceanographic data for years. Not a model prediction, not a simulation output. Actual observational data, temperature records, salinity measurements, ocean current velocity readings collected by an array of moored instruments stretched across the Atlantic Ocean at 26.5 degrees north L attitude, a monitoring system called RAPID that has been continuously recording the state of the Atlantic Ocean's circulation since 2004. The dataset is 17 years long. In the context of ocean circulation, which operates on timescales of decades to centuries, 17 years is a narrow window. But it is the most continuous, most direct, most instrumentally rigorous record of the Atlantic meridional overturning circulation ever assembled. And what the Potsdam team is finding when they analyze it is not subtle. The AMOC, the Atlantic meridional overturning circulation, the vast system of ocean currents that moves warm surface water northward from the tropics and returns cold deep water southward. The system that gives Western Europe its mild climate and that drives the exchange of heat, carbon, and nutrients across the entire Atlantic basin, is weaker than at any point in the observational record. Not slightly weaker. Not statistically borderline. The flow rate, measured by the RAPID array in recent years, is approximately 15% below the long-term average estimated from proxy records spanning the past 600 years. The current is slowing, and the rate of slowing, the trajectory visible in THE's 17-year dataset, is inconsistent with natural variability. It is consistent with something that the climate models have been predicting for decades, that previous generations of oceanographers argued about fiercely in academic journals, and that the scientific consensus has been approaching with increasing reluctance because the implications are so large. The AMOC is losing strength, and the most parsimonious explanation for the data is the one that the researchers in that Potsdam office have spent careers hoping they would not have to confirm. Fresh water from the melting Greenland ice sheet, pouring into the North Atlantic at rates that are accelerating as global temperatures rise, is diluting the salty, dense surface water that drives the AMOC circulation. Less dense water sinks less radial Y. Less sinking means less circulation. Less circulation means less heat transport. And less heat transport means a cascade of regional and global climate changes that the models have been projecting for decades, but that the data, until recently, could not confirm were already underway. The paper is published in Nature Climate Change in August 2021. The title is Precise Observation-Based Early Warning Signals for a Collapse of the Atlantic Meridional Overturning Circulation. Early warning signals, not a prediction, not a model output. A detection, in the actual data, in the measurements from real instruments in the real ocean, of the statistical fingerprints that dynamical systems theory predicts will appear in the behavior of complex systems, approaching a tipping point. The ocean current that has kept Western Europe's climate mild for thousands of years, the current that distributes heat, carbon, and rainfall across the entire Atlantic basin, that influences monsoon patterns in West Africa and South Asia, that affects sea level along the eastern coast of North America, was showing, in the instrumental record, the specific mathematical signatures of a system approaching catastrophic reorganization. The reaction within the climate science community was not uniform. Some researchers, including several of the authors of the RAPID dataset analyses, argued that the early warning signal methodology applied by the Potsdam team was not well validated for ocean circulation systems, that the statistical signatures identified could reflect natural multidecadal variability rather than proximity to a tipping point, and that the paper's framing overstated the certainty of its conclusions. Others, including researchers who had been studying AMOC variability for decades, argued that the finding was consistent with multiple independent lines of evidence. The proxy record from sediment cores and ice cores that showed AMOC at its weakest in a millennium. The fingerprint analysis of sea surface temperature patterns that revealed the circulation's slowdown even before the rapid array provided direct measurements. The freshwater budget calculations showing that Greenland melt is adding freshwater to the North Atlantic at rates the models had not expected to see until mid-century. The debate, vigorous, technical, conducted in the pages of major scientific journals, is ongoing. It has not been resolved. The question of whether the AMOC is approaching a tipping point, a threshold beyond which its collapse would be rapid, self-reinforcing, and effectively irreversible on human timescales, is one of the most actively contested and most consequential questions in contemporary climate science. This video is about that question. Not about the settled science of AMOC current state, which shows a weakening circulation with high confidence, but about what that weakening means, how far the system is from a tipping point, what a collapse would actually produce in terms of regional and global climate changes, and why the uncertainty about the timing of potential collapse is not a reason for complacency, but rather reflects the specific challenge of predicting the behavior of complex systems near critical thresholds. The central contradiction of this story is geographically precise and historically documented. The Atlantic meridional overturning circulation is the reason that London is warmer than Labrador, despite being at a similar latitude. It is the reason that Western Europe is habitable and agriculturally productive at latitudes that, in North America, produce subarctic conditions. It is the reason that the monsoon systems of West Africa and South Asia deliver rainfall to billions of people on roughly predictable seasonal schedules. It is, in the most direct physical sense, one of the primary mechanisms by which the atmosphere and ocean distribute the sun's energy across the planet in the pattern that the last 12,000 years of human civilization was built around. And the observational data, the instrument records, the proxy reconstructions, the fingerprint analyses, the freshwater budget calculations, consistently shows that this mechanism is weaker now than at any point in at least the last 1,000 years, and possibly much longer. The contradiction is not between models and observations. The models predicted this. The contradiction is between the scale of what the data is showing and the pace at which that information has entered public understanding and policy consideration. By the end of this video, you will understand what the AMOC is, how it works, and why it matters for the climate of regions that are home to billions of people. You will understand what the current observational data shows about its state, with its uncertain ties and its contested interpretations. You will understand what a partial weakening, the trajectory already underway, would mean for regional climates, sea levels, and rainfall patterns. And you will understand what a collapse, the scenario that the early warning signal literature is concerned with, would mean, and why the uncertainty about its likelihood is not the same as low probability. What physical mechanism drives the AMOC, and what does freshwater from Greenland do to that mechanism? What does the observational data, not the models, the actual measurements from the real ocean, show about the AMOC current state? How does a system collapse in oceanography? What does tipping point actually mean, and why is the transition potentially irreversible? What would a weakened or collapsed AMOC mean for the specific regions that depend on it? Western Europe, the Eastern United States, West Africa, South Asia. Why is the range of scientific opinion on collapse probability so wide? from unlikely this century to possible within decades. And what would resolve the disagreement? And what does the EMOC story tell us about the specific challenge of governing for risks that are large, uncertain in timing, and effectively irreversible once they materialize? This is not a video about climate doom. It is a video about a specific physical system, one of the most important components of the Earth's climate machinery, whose current behavior is documented, whose trajectory is concerning, and whose potential future states range from uncomfortable to catastrophic depending on the choices made in the next several decades. We stay in the data. We represent the scientific uncertainty honestly. We do not reach beyond what the evidence supports. What the evidence supports is already serious enough to warrant the full attention of anyone who lives on this planet. If evidence-driven science on the most consequential questions facing human civilization is what you're looking for, subscribe to Galaxy Pulse. Every video follows the data. Now, back to the Atlantic. To understand why the EMOC current weakening is cause for genuine scientific concern, rather than routine variability, why the finding that the circulation is at its weakest in over a millennium has the specific significance it has, we need to understand what the EMOC is, how it works, and what role it plays in the global climate system. The Atlantic meridional overturning circulation is not a single current. It is a system, an interconnected network of ocean flows that collectively move an enormous quantity of water, heat, salt, carbon dioxide, and nutrients through the Atlantic Ocean in a roughly continuous loop. The system's basic structure is a conveyor belt that operates in 3 dimensions. Warm, salty surface water flows northward through the Atlantic from the tropics toward the North Atlantic and the Nordic Seas. This water releases heat to the atmosphere, a low Ng, the way, warming the land masses on either side of the North Atlantic, particularly Western Europe. As the water reaches high latitudes and cools, it becomes denser. Cold water is denser than warm water, and salty water is denser than fresh water, and eventually dense enough to sink to the deep ocean in specific regions called convection zones, primarily in the Labrador Sea, the Erminger Sea, and the Nordic Seas. The sunk water then flows southward along the deep ocean floor, eventually returning to the surface in the Southern Ocean and the Pacific through a process called upwelling. And the cycle begins again. The volume of water moved by this system is staggering. At its reference monitoring latitude of 26.5 degrees north, the latitude where the rapid array provides continuous measurements, the EMOC transports approximately 17 to 18 million cubic meters of water per second, a number called 17 to 18 sverdrups. 1 sverdrup is 1 million cubic meters per second. For reference, all the world's rivers combined discharge approximately 1 sverdrup into the oceans. The EMOC moves 17 to 18 times the combined freshwater discharge of every river on Earth in ocean water, continuously, as part of its normal operation. The heat transported northward by this water movement is similarly enormous. The EMOC carries approximately 1.3 petawatts of heat northward across the 26.5 degree north latitude line, 15 watts, roughly equivalent to the output of 1 million large power plant s. This heat is released to the atmosphere over the North Atlantic and Western Europe, and its effect on regional climate is large enough to be the dominant reason for the climate difference between Europe and North America at the same latitudes. London is at approximately 51 degrees north. The equivalent latitude in North America is just north of Calgary, Alberta, a city that experiences temperatures of -20 to -30 Celsius in winter. That is in the southern fringe of the boreal F-Orst, that has a subarctic climate by any standard definition. London's average January temperature is approximately 5 degrees Celsius. The difference, roughly 25 to 30 degrees of average winter temperature at the same latitude, is primarily a consequence C of the heat delivered to the North Atlantic atmosphere by the AMOC. Paris is at 49 degrees north. Winnipeg, Manitoba, at the same latitude, has average January temperatures of -16 Celsius. Paris averages approximately 5 degrees Celsius. Bergen, Norway, is at 60 degrees north, the same latitude as the southern tip of Greenland, the Aleutian Islands of Alaska, the coast of Siberia. Bergen's average January temperature is approximately 3 degrees Celsius. The equivalent latitude in North America produces conditions incompatible with agriculture for most of the year. This is the AMOC gift to Western Europe, a climate that is 12,000 years old, that has been stable throughout the entirety of recorded history, that the agricultural systems, population distributions, and infrastructure of a continent of 450 million people were built around. The AMOC influence extends beyond Western Europe. Its northward heat transport affects the position of the intertropical convergence zone, the belt of rising air near the equator that drives the rainfall patterns of the tropics. When the AMOC is strong, the it sits in its current position, delivering rainfall to the Sahel region of West Africa and to the South Asian monsoon system. When the AMOC weakens, models and paleoclimate evidence both show that the it shifts southward, a shift that reduces raw infall in the Sahel and affects the intensity and timing of the Asian monsoon, with consequences for the food and water security of billions of people. The AMOC also affects sea level along the eastern coast of North America. The current's northward flow creates a slope in the sea surface. Water is slightly higher on the seaward side of the current than on the coastal side. When the current weakens and his slope reduces, sea level along the eastern U.S. and Canadian coast rises by an amount beyond the global average sea level rise, driven by ice melt and thermal expansion. Cities from Miami to Boston to Halifax experience above average sea level rise when the AMOC weakens, a direct, measurable, currently ongoing consequence of the circulation's decline. Here is what the AMOC is supposed to look like in terms of variability. Like all components of the climate system, the AMOC is not perfectly constant. It varies on timescales from seasonal to decadal, driven by variations in wind stress, ocean heat content, freshwater input, and the internal dynamics of the coupled ocean-atmosphere system. These natural variations have a characteristic amplitude, a range of fluctuation around a long-term mean, that can be estimated from the instrumental record and from proxy reconstructions going back thousands of years. The pre-industrial AMOC, the circulation operating before significant anthropogenic greenhouse gas forcing, had a flow rate estimated from proxy records at approximately 18 to 20 sverdrups at the rapid monitoring latitude, with natural variability of perhaps 1 to 2 sverdrups around this mean on decadal timescales. The system was not static, but it was stable, fluctuating within a bounded range without large directional trends. What the modern observational record shows is not fluctuation around a stable mean. The rapid array data, since continuous measurements began in 2004, shows a mean flow rate approximately 15% below the proxy estimated pre-industrial baseline, corresponding to a weakening of approximately 2 to 3 sverdrups below the long-term average. The sea surface temperature record, going back to the late 19th century, shows a cold anomaly developing in the North Atlantic subpolar gyre, the region where AMOC sinking occurs. That is the expected fingerprint of a weakening circulation, failing to deliver its normal heat complement to the high-latitude North Atlantic. And the proxy record, the reconstruction of past amok strength from sediment cores, coral records, and ice cores going back 600 years, shows the current level of amok weakness as unprecedented in the entire record. Not at the weak end of the natural variability range, beyond it, in territory that has not been visited since before the medieval warm period, before the Viking Age, before the construction of the great medieval European cathedrals. The contrast between the expected natural variability around a stable pre-industrial mean and the directional weakening trend visible in the modern observational record is the gap where the scientific concern lies. It is a contrast, not between model predictions and observations. The models predicted a weakening amok under greenhouse forcing. It is a contrast between the pre-industrial baseline and the current state that indicates something outside the range of natural variability is driving the change. That something is freshwater from the melting Greenland ice sheet, a freshwater flux that is adding approximately 1 trillion tons of meltwater to the North Atlantic annually in recent years, diluting the salty surface water that needs to become dense to sink, slowing the overturning circulation at its fundamental driving mechanism. To understand why the amok is weakening, and why that weakening could, under certain conditions, become self-reinforcing and rapid, we need to understand the specific physics of the circulation's driving mechanism. The amok runs on density differences. The fundamental driver is that cold, salty water is denser than warm, fresh water. The circulation moves surface water northward, where it cools and becomes denser. When the water becomes dense enough, it sinks. The sea king drives the return flow at depth. The return flow at depth drives the northward surface flow. The whole system is self-sustaining as long as the sinking at the northern end continues. The sinking, called deep water formation, is the critical, vulnerable step in the system. It happens in specific locations: the Labrador Sea, south of Greenland, the Erminger Sea, between Greenland and Iceland, and the Nordic Seas, north of Iceland. In these locations, surface water that has been progressively cooled and concentrated in salt by evaporation along its northward journey finally reaches the density threshold required for sinking. When this happens, parcels of water plunge to depths of 2 to 4 kilometers and spread southward along the ocean floor. For the sinking to happen, the surface water must be salty enough. Salinity is the property that provides the density boost that cold water alone sometimes cannot. In the Nordic seas, for example, the water never gets cold enough to sink on the basis of temperature alone. It is the high salinity, accumulated along the northward journey through the subtropical Atlantic, where evaporation concentrates salt in the surface water, that provides the critical density margin. Now, add freshwater from Greenland. The Greenland ice sheet is the second largest ice body on Earth, containing enough water to raise global sea levels by approximately 7 meters if fully melted. It has been losing mass at an accelerating rate since the 1990s. Current estimates from GRACE satellite gravity measurements show Greenland losing approximately 280 billion tons of ice per year, a rate that has been approximately doubling every decade since the 1990s. This meltwater enters the North Atlantic primarily in the regions surrounding Greenland, the subpolar North Atlantic, the Labrador Sea, the Erminger Sea, exactly the regions where deep water formation drives the amok. Fresh water is less dense than salt water. When freshwater mixes with the salty surface water of the subpolar North Atlantic, it reduces the salinity and therefore the density of that water. Reduced density water sinks less readily. Less sinking means less deep water formation. Less deep water formation means a weaker amok. This is not a subtle or speculative mechanism. It is straightforward thermodynamics applied to a known forcing. Fresh water from a melting ice sheet entering the ocean in the exact location where the ocean's sensitivity to fresh water is highest. The critical question. The question that determines whether the amok weakening is a gradual, manageable response to forcing that will stabilize when greenhouse emissions stabilize, or whether it is a progressive approach to a tipping point beyond which the system reorganizes catastrophically, is whether the circulation has two stable states, or one. The concept of bistability is central to understanding why the amok collapse question is treated differently from most climate projections. Most components of the climate system respond to forcing in a roughly linear, reversible way. More forcing produces more response, and reducing the forcing allows the system to return approximately to its previous state. Global mean temperature responds ugly linearly to greenhouse gas concentration, more greenhouse gases, higher temperature, and in principle, reducing greenhouse gas concentrations would allow temperatures to return toward the previous baseline. Some components of the climate system do not behave this way. They have multiple possible stable states, configurations that the system can maintain against perturbations, and the transition between states, once triggered, can be rapid, self-reinforcing, and effectively irreversible on human timescales. These are tipping point systems, and the amok is the most studied example in climate science. The physical basis for amok bistability was first described theoretically by the oceanographer Henry Stommel in 1961, decades before the modern observational record existed. Stommel showed mathematically that a simplified model of the thermohaline circula tion has two stable equilibria. A strong circulation state, where salt transport maintains the density difference required for deep water formation, and a weak, or collapsed state, where freshwater dilution has reduced salinity enough that deep water formation stops and the circulation shuts down. The critical insight is that the transition between states can be self-reinforcing. As the amok weakens, it transports less salty water northward, which means the subpolar North Atlantic receives less salt from the tropics. Less salt means lower density. Lower density means less sinking. Less sinking means a weaker circulation. A weaker circulation means less salt transport northward. The feedback loop is positive. Each reduction in circulation strength tends to produce further reduction. This positive feedback does not operate in isolation. There are stabilizing feedbacks as well. Changes in temperature, wind patterns, and atmospheric circulation that partly offset the destabilizing freshwater effect. The question of whether the net feedback is destabilizing, whether the amok in its current state is closer to a tipping point than to a stable configuration, is the central scientific question of the amok collapse literature. Think of it as a ball in a landscape with two valleys separated by a hill. The ball can sit stably in either valley. Pushing the ball toward the hill requires energy. But once the ball reaches the hilltop, the tipping point, it rolls down the other side under its own momentum, regardless of what you do. The question is, how close is the ball to the hilltop? And is the slope it is currently on taking it closer to or further from the hilltop? The amok weakening observed in the instrumental and proxy record is the ball moving. The question is, in which direction? Here is where the amok story acquires a historical dimension that makes the theoretical tipping point concept concrete and specific. The last time the amok underwent a substantial collapse was approximately 12,900 years ago. The event is called the Younger Dryas. a rapid and severe cold period that interrupted the warming that had been underway since the end of the last glacial maximum. Within decades, possibly within years, northern Europe went from temperatures comparable to the modern climate back to near glacial conditions. Average temperatures in Greenland dropped by approximately 10 to 15 degrees Celsius in a geological instant. The cause? A catastrophic release of fresh water into the North Atlantic from the melting ice sheets of the last glaciation. As the ice sheets retreated northward, they impounded enormous lakes of meltwater behind ice dams. When those ice dams failed, possibly catastrophically, in events called glacial lake outburst floods, they released volumes of fresh water into the North Atlantic sufficient to overwhelm the amok salt transport and shut it down. The shutdown lasted approximately 200 years. When it ended, when the freshwater forcing that had sustained it weakened enough, the amok abruptly restarted, and temperatures in northern Europe rose back to near modern values within decades. The Younger Dryas is recorded in ice cores, sediment cores, pollen records, and other paleoclimate proxies with extraordinary clarity. It is the most dramatic example of abrupt climate change in the geological record of the Holocene era. And it was caused by freshwater forcing of the North Atlantic, the same mechanism that is currently operating, at a lower rate, from Greenland ice sheet melt. The comparison is not exact. The freshwater forcing of the Younger Dryas was almost certainly larger and faster than the current Greenland melt contribution. The background climate state was different. The world was just emerging from an ice age, with more ice to melt and different ocean temperature distributions. The amok, in its pre-industrial Holocene state, may have been more stable than the amok at the end of the last glaciation. But the comparison is not irrelevant either. It demonstrates that the amok bistability is not a theoretical construct. It is a physical property of the real ocean that has been realized at least twice in the geological record of the past 20,000 years. The ball has been over the hill before. It crossed in both directions, and the forcing that drove it, freshwater, into the North Atlantic, is the same forcing that is currently increasing. The mechanism is known. The historical precedents are documented. The current trajectory of freshwater forcing is upward and accelerating. The observational data shows the circulation at its weakest in over a millennium. What the science has been arguing about vigorously in the pages of the most prestigious journals, between researchers who agree on the physical mechanism but disagree on how close the system is to the tipping point, is the question of timing. And it is in that argument, in the specific details of what the models show and what the data constrains, that the most important information for understanding our current situation lies. The 2021 Potsdam paper by Nicholas Bowers, the paper that detected what it described as early warning signals for amok collapse in the observational record, deserves careful examination, because it is both the most provocative recent finding in the amok literature and the most contested. The methodology Bowers applied comes from dynamical systems theory, the mathematical framework for understanding how complex systems behave as they approach critical transitions. And in this framework, a system approaching a tipping point exhibits specific statistical behaviors. Its fluctuations become larger in amplitude, a phenomenon called critical slowing down's associated variance increase. Its fluctuations become more correlated in time, autocorrelation increase, and its response to external perturbatio ns becomes slower and more persistent, critical slowing down itself. These behaviors are observable in the time series of the system's state variables before the transition occurs, and they provide a statistical early warning that the system is approaching a threshold. Bowers applied this framework to 8 different observational proxies for amok strength, including sea surface temperature fingerprints of amok behavior, salinity records from the subpolar North Atlantic, and ocean color data related to amok-driven upwelling, spanning the period from approximately 1870 to 2020. In 7 of the 8 proxies, he found statistically significant increases in both variance and autocorrelation over the 20th century. The specific signatures that the early warning signal framework predicts for a system approaching a critical transition. The finding is significant for 2 reasons. First, it is based on observational data rather than model output. The statistical signatures are present in the actual measured state of the ocean, not in a simulation. Second, the fact that 7 independent proxies show the same signatures reduces the probability that any individual result is a statistical artifact. The methodological challenges are equally significant. The early warning signal methodology has not been validated specifically for the amok. It has been applied successfully to other systems, ecological transitions, financial markets, epileptic seizures, but its applicability to ocean circulation is disputed. Critics argue that the statistical signatures Bowers identified could reflect natural multidecadal ocean variability, the Atlantic multidecadal oscillation, for example, rather than proximity to a tipping point. They argue that the proxy records used are not all independent. Some may reflect the same underlying physical processes, making the apparent convergence of results less statistically compelling than it appears. A 2022 paper by a team including several senior oceanographers, published in Nature Climate Science, challenged the Bowers paper's conclusions directly, arguing that the specific proxies used and the statistical methodology applied were not appropriate for detecting amok tipping point proximity, and that the results should be interpreted as reflecting a MOC variability rather than tipping point approach. The Bowers team responded, and the methodological debate continues in the literature. What the debate does not challenge: the underlying finding that the amok is currently weaker than at any point in the observational and proxy record of the past millennium. That finding is not contested. What is contested is the interpretation of the weakening, whether it reflects proximity to a tipping point or a forced response that will stabilize as the freshwater forcing stabilizes. This distinction matters enormously for risk assessment. A forced response that stabilizes implies that aggressive emissions reduction and stabilization of the Greenland melt could prevent further weakening and allow the circulation to partially recover. A system approaching a tipping point implies that there may be a threshold beyond which stabilization of the forcing is insufficient to prevent collapse, that the positive feedbacks, once triggered, carry the system to the collapsed state, regardless of what happens to the external forcing. The data does not currently distinguish between these scenarios with confidence. The models disagree about which is more likely, and the implications of the 2 scenarios for climate risk are sufficiently different that the disagreement matters in a practical, policy-relevant sense. The range of scientific opinion on amok collapse probability is wider than for almost any other component of the climate system, and understanding why requires understanding the specific challenges of modeling ocean circulation. The IPCC 6th Assessment Report, published in 2021, assessed the probability of an abrupt amok collapse this century as a low, but gave a medium confidence finding that the amok would weaken over the 21st century under all emissions scenarios. A low probability, in IPCC language, does not mean negligible. It means roughly 10% or less, for an event with the consequences that amok collapse would produce. A 10% probability over a century is a risk that most risk management frameworks treat as requiring serious attention. But the range within the scientific community spans from a very unlikely this century to a possible within decades, and the sources of this disagreement are instructive. The primary source of disagreement is the treatment of freshwater forcing from Greenland and other Arctic sources. The CMIP-6 models, the state-of-the-art coupled climate models used for the IPCC assessment, generally project a gradual EMOC weakening over the 21st century under high emissions scenarios, reaching perhaps 15 to 30% below current strength by 2100, but not collapsing. These models have been criticized by several research groups for having EMOC systems that are too stable, that their representation of the ocean's salt feedback. The mechanism by which EMOC weakness leads to less salt transport and potentially more weakness does not adequately capture the instability that Stommel's theoretical analysis and paleoclimate evidence suggest is physically present. A 2023 study by a Danish team at the University of Copenhagen used a different approach. Instead of running comprehensive climate models, they constructed a simplified model specifically designed to capture the EMOC salt advection feedback, tuned to reproduce the statistical properties of the observed sea surface temperature fingerprint. This model, simpler than the CMIP-6 models, but more explicitly designed to capture the bistability, projects EMOC collapse within this century under moderate to high emissions scenarios, with a probability distribution suggesting collapse possible as early as the mid-2020s to 295 under different scenarios. The Copenhagen study was immediately controversial. Other researchers pointed out that simplified models, while useful for exploring specific feedbacks, may miss the stabilizing processes captured by comprehensive climate models. The CMIP-6 community argued that their model's EMOC stability was not necessarily a flaw, that the comprehensive models capture interactions between the EMOC, the atmosphere, the sea ice, and the rest of the ocean that simplified models omit. This disagreement is not resolvable with currently available data. The critical question: does the real EMOC have a tipping point within the range of anthropogenic forcing? And if so, how close is the current state to that tipping point? Requires knowing the shape of the EMOC stability landscape in a way that neither the observational record nor the models can currently provide with confidence. What both camps agree on: the EMOC is weaker than it was, the freshwater forcing driving the weakening is increasing, and the consequences of collapse would be severe and largely irreversible on human timescales. The disagreement is about probability, not about mechanism or consequence. The consequences of EMOC weakening, whether gradual or abrupt, are not uniform across the planet. They are strongly regional, affecting different parts of the world in different ways and on different timescales. Understanding the regional specificity is essential for understanding both the severity of the risk and its distribution across human populations. The most direct consequence of EMOC weakening for Western Europe is cooling, a reduction in the heat currently delivered to the North Atlantic atmosphere by the warm surface water transported northward. Current projections suggest that gradual EMOC weakening over the 21st century would offset a portion of the greenhouse gas-driven warming that would otherwise occur in Western Europe, not producing net cooling below current temperatures in the gradual weakening scenario, but producing cooling relat-ive to the baseline that would be experienced with a full-strength EMOC. In the abrupt collapse scenario, the cooling would be dramatically larger. Paleoclimate evidence from the Younger Dryas suggests that EMOC collapse can produce regional cooling of 5 to 10 degrees Celsius in northern Europe on timescales of decades, superimposed on whatever background warming greenhouse gases have produced. The combination is particularly challenging to model. global mean temperature rising due to greenhouse forcing, while the North Atlantic and Western Europe cool due to EMOC weakening. The two forcings oppose each other, and the net effect depends on their relative magnitude at any given time. Under most model projections, greenhouse warming dominates in the long run. Even with a collapsed EMOC, Western Europe would eventually warm above current temperatures. But the trajectory through the transition period would involve significant and rapid regional climate disruption. Beyond temperature, EMOC weakening affects precipitation patterns in Western Europe. The current warm North Atlantic SSDs drive atmospheric moisture and storm track patterns that produce the mild, relatively moist climate of the British Isles and northwest Europe. Weakening of these SSDs is projected to shift storm tracks and reduce precipitation in some regions, while potentially increasing it in others. Agricultural systems optimized for current precipitation patterns would face significant disruption. The eastern coast of North America faces a specific and already measurable consequence of EMOC weakening: above average sea level rise. The mechanism, the reduction of the sea surface slope maintained by the northward current flow, produces sea level rise along the U.S. East Coast that exceeds the global average by a factor of 2 to 4. Cities including Miami, New York, Boston, and Halifax are in the zone of accelerated sea level rise driven by EMOC weakening, superimposed on the global sea level rise from ice melt and thermal expansion. Miami is already experiencing chronic tidal flooding, nuisance flooding during high tides even without storm events, at rates that are increasing as sea level rises. The combination of global sea level rise and the EMOC-driven above-average rise along the East Coast is compressing the timeline for infrastructure adaptation in coastal cities by decades compared to the global average trajectory. The EMOC influence on the intertropical convergence zone, the atmospheric circulation belt that drives tropical rainfall, means that EMOC weakening directly affects the rainfall patterns of West Africa. The Sahel region, a semi-arid zone south of the Sahara that is home to more than 135 million people and that has experienced catastrophic drought events historically, is particularly sensitive to shifts driven by North Atlantic temperature changes. Paleoclimate evidence shows that periods of weak EMOC correspond to reduced Sahel rainfall. The West African monsoon weakens when the North Atlantic is cooler than normal, because the thermal gradient that drives the monsoon circulation is reduced. Projections of EMOC weakening under greenhouse forcing include reductions in Sahel rainfall that, in the more severe scenarios, approach the conditions of the devastating Sahel droughts of the 1970s and 1980s that contributed to famines affecting tens of millions of people. The South Asian monsoon, the seasonal rainfall system that delivers approximately 70 to 90% of the annual precipitation in South Asia to approximately 1.5 billion people, is driven primarily by land-sea temperature contrasts over the Indian and subcontinent during summer. It is also influenced, through complex teleconnections in the global atmospheric circulation, by North Atlantic sea surface temperature patterns. The precise relationship between EMOC strength and South Asian monsoon intensity is not as clearly established as the West African connection, and the models show more uncertainty in this teleconnection. But several model studies suggest that EMOC weakening produces a reduction in South Asian monsoon rainfall, a finding that, given the food and water security implications for South Asian populations, is one of the more concerning potential global consequences of EMOC collapse. The EMOC transports significant heat into the Arctic Ocean through its connection with the Nordic Sea's circulation. Weakening of the AMOC would reduce this heat transport, potentially allowing sea ice in the Barents Sea and Greenland Sea to expand. A counterintuitive effect in the context of overall Arctic warming. However, this sea ice expansion would interact with the broader Arctic system in complex ways, including effects on the Arctic Oscillation and the polar vortex that influence winter weather patterns across the northern hemisphere. The net effect of AMOC weakening on Arctic climate is not a simple story of more or less ice. It is a complex reorganization of northern hemisphere atmospheric circulation patterns that the current generation of models represents with significant uncertainty. The conservative position, broadly consistent with the IPCC's 6th Assessment Report's assessment, holds that the AMOC will weaken gradually over the 21st century under high-emissions scenarios, but will not collapse. The CMIP-6 models, which are THE most physically comprehensive representations of the climate system available, generally produce this outcome. Under this framework, the consequences of AMOC weakening are serious but manageable. Accelerated sea level rise on the U.S. East Coast, Region L cooling in northern Europe that partially offsets greenhouse warming, reduced rainfall in the Sahel. These are significant impacts that require adaptation planning, but they are not catastrophic in the sense of producing rapid, irreversible civilizational disruption. The weakness of this framework. The CMIP-6 models may systematically underestimate the AMOC sensitivity to freshwater forcing because of representation errors in the ocean component models. The salt advection feedback, the mechanism that gives the AMOC ITS bistability, is difficult to capture accurately in models with the resolution constraints of current comprehensive climate models. And there is some evidence in model evaluation studies that the CMIP-6 model's AMOC is more stable than paleoclimate. Evid suggests the real AMOC should be. The moderate position holds that the AMOC weakening is real and potentially severe, that the collapse risk within this century is non-negligible, and that the uncertainty in current models is large enough that planning for the possibility of abrupt transit is warranted, even if the most likely outcome is gradual weakening. This position is consistent with treating the AMOC as a potential tipping element in the Earth's climate system, an element whose tipping could be triggered by forcing within the range of plausible anthropogenic scenarios. This framework emphasizes the asymmetry of the risk. The costs of preparing for a collapse that does not occur are moderate, unnecessary adaptation investment, policy measures that prove unnecessary, while the costs of failing to prepare for a collapse that does occur are potentially catastrophic and irreversible. Under standard risk management frameworks, this asymmetry argues for precautionary treatment of even relatively low probability collapse scenarios. The most alarming position in the scientific literature, represented by the Copenhagen Simplified Model Study and by several research groups working on AMOC bistability, holds that the current observational evidence, including the early warning signals detected by bowers, is consistent with the AMOC being within the range of forcing that could trigger collapse within decades rather than centuries. This position argues that the comprehensive climate model's systematic underrepresentation of the AMOC bistability makes them unreliable guides to collapse risk, and that the combination of observational evidence, simplified model results, and paleoclimate analogs warrants treating near-term collapse as a scenario that deserves serious weight in risk assessment (NTS). This position is a minority view among professional oceanographers, and it carries the significant uncertainty inherent in extrapolating from simplified models and statistical early warning signals to predictions about a complex physical system. But it is held by credentialed researchers publishing in major journals, and the physical mechanisms it invokes are real and well understood. There is a specific quality to the way the amok risk presents itself to human understanding that is different from most climate risks, and it is worth naming directly. Most climate risks scale with emissions in roughly continuous ways. More emissions produce more warming, more sea level rise, more extreme weather. The relationship between action and outcome is approximately linear. Reduce emissions by 30%, GT, approximately 30% less of the projected impact. This linearity, even though the absolute scale of the impacts is enormous, at least preserves the logic of incremental action. Every ton of carbon dioxide not emitted is a fraction of impact avoided. The amok tipping point scenario does not have this property. If the amok is a bistable system with a tipping point, there is a threshold below which the freshwater forcing can be absorbed without triggering collapse, and above which positive feedbacks carry the system to the collapsed state, regardless of subsequent forcing changes. Below the threshold, emissions reduction helps. At or above the threshold, the system's internal dynamics take over, and the outcome is determined by the system's physics, not by subsequent human choices. This means the amok risk cannot be managed incrementally in the way that continuous climate risks can. It requires determining whether a threshold exists, approximately where it is, and whether current forcing is approaching it, questions that the current science cannot answer with confidence. And it means that waiting for better scientific certainty before acting carries the risk of waiting past the threshold, of reaching the point at which the choice is no longer available. This specific structure, a potentially irreversible threshold under genuine scientific uncertainty, where the cost of waiting for certainty could be crossing the threshold before the certainty arrives, is one of the most difficult problems in the governance of long-term risks. It is the specific problem that the amok presents. Remember what we asked at the start. What does the observational data actually show about the amok current state? How does the tipping point mechanism work, and how close might the system be to crossing it? And what would the consequences of collapse be for the specific regions and populations that depend on the circulation's heat transport for their climate, their agriculture, and their infrastructure? After everything we have examined, the physical mechanism of the amok and why freshwater disrupts it, the observational evidence from the rapid array and the proxy record, the theoretical framework of bistability and tipping points, the historical precede NT of the Younger Dryas, the regional consequences of weakening and collapse across Europe, North America, West Africa, and South Asia. Here is where the honest accounting stands. The amok is weaker now than at any point in the past millennium. The freshwater forcing driving the weakening is increasing as the Greenland ice sheet melts at an accelerating rate. The theoretical mechanism for a tipping point is well established in the physics of the system. The paleoclimate record confirms that tipping has occurred in the past under similar forcing. The models disagree about whether a tipping point will be crossed this century. The early warning signal analysis suggests the system may be approaching a critical transition. The comprehensive climate models suggest gradual weakening without collapse. The honest summary. The amok is a system with known tipping point physics, currently being pushed by a known and increasing forcing, showing observational signs of weakening at unprecedented rates, with a scientific community that disagrees about collapse probability by a margin that reflects genuine uncertainty in the models rather than a settled answer in either direction. That specific combination, known mechanism, increasing forcing, observable weakening, genuine uncertainty about collapse probability, is the amok risk profile. And it is a risk profile that requires serious attention regardless of which end of the uncertainty range proves to be closer to the truth. The public coverage of amok weakening has been shaped by a recurring pattern. Individual papers reporting alarming findings receive significant media attention, generating a round of amok collapse imminent headlines, followed by commentary from other scientists expressing more cautious interpretations, generating a round of amok collapse overstated coverage. This oscillation has produced a public understanding of the issue that is poorly calibrated, alternating between alarm and reassurance, without a clear sense of what the scientific evidence actually shows in aggregate. The most significant finding that has received inadequate public coverage is the spatial heterogeneity of the amok weakening signal. The rapid array measures the total amok transport at a single latitude, 26.5 degrees north. This is the most direct measurement of the circulation's overall strength. But the weakening is not spatially uniform. The rapid data, combined with Argo float measurements and altimetry data from satellite observations, shows that the weakening is concentrated in specific components, OF, the circulation, particularly in the upper, warm water return from the subtropical gyre, and in the deep western boundary current that carries recently formed North Atlantic deep water southward. This spatial specificity is scientifically important because it constrains the mechanism of the weakening. If the weakening were simply the result of reduced deep water formation in the subpolar North Atlantic, the direct freshwater effect, it would show most prominently in the deep water component of the rapid transport. The observed concentration of weakening in specific components suggests a more complex picture, possibly involving changes in wind-driven circulation in the subtropical Atlantic in added ion to the thermohaline component. Understanding the relative contributions of different mechanisms to the total weakening is essential for projecting future changes, and the public coverage, which focuses almost entirely on the thermohaline mechanism and the Greenland melt forcing, has not conveyed this complexity. A second finding that received inadequate coverage: the detection by Bowers and colleagues, in a 2023 follow-up paper, of coherent early warning signals not just in amok proxies, but in the coupled atmosphere-ocean system across the North Atlantic. The 2021 paper detected early warning signals in ocean state variables. The 2023 follow-up found corresponding signals in atmospheric variables, sea level pressure, wind patterns, that respond to and interact with amok changes. The coherence of early warning sign ALs across multiple, physically coupled components of the system reduces the probability that the signals are statistical artifacts of any individual proxy series, and strengthens the case that they reflect real dynamical behavior of the coupled system. A third finding: the 2023 reassessment of the paleoclimate record of amok strength by a consortium of proxy data groups, which extended the record backward to approximately 10,000 years before present. The extended record shows that the current level of a MOC weakness is not just unprecedented in the past 600 years. It may be unprecedented in the past several thousand years, with the circulation currently at its weakest since the early Holocene, when the ice sheets were still significantly larger, and the freshwater forcing from ice melt was correspondingly higher. This finding strengthens the case that the current weakening is outside the range of natural variability and reflects an anthropogenically forced change. The freshwater forcing driving the amok weakening is not a future projection. It is a current, measured, accelerating process. Understanding its scale and trajectory is essential for understanding the amok risk. The Greenland ice sheet is losing mass at a rate that has increased approximately sixfold since the 1990s. In the 1990s, Greenland was losing approximately 34 billion tons of ice per year. In the 2000s, the rate increased to approximately 215 billion tons per year. In the most recent decade, the rate has been approximately 280 billion tons per year, with significant year-to-year variability. The total mass loss since 1992 has been approximately 5,000 gigatons, equivalent to approximately 14 millimeters of global sea level rise from Greenland alone. The mass loss occurs through two primary mechanisms: surface melt. The direct melting of the ice sheet surface by atmospheric warming has been increasing as Arctic temperatures rise at rates approximately 4 times the global average, a phenomenon called Arctic amplification. Marine ice loss. The calving of glaciers that terminate in the ocean, accelerated by ocean warming that melts the ice from beneath, has also increased, and satellite-based tracking of individual outlet glaciers shows that several of the largest have accelerated their flow to the ocean by factors of 2 to 3, compared to the 1990s. The freshwater enters the North Atlantic primarily in two forms: as meltwater runoff from the surface of the ice sheet, liquid freshwater, entering the ocean directly, and as icebergs calved from marine terminating glaciers, which melt in the ocean over timescales of days to weeks. Both forms reduce the salinity of the subpolar North Atlantic. The annual freshwater flux from Greenland into the surrounding ocean, approximately 1,000 cubic kilometers of water per year in recent years, is a small fraction of the total water volume of the subpolar North Atlantic, but it is not uniformly mixed. The freshwater enters preferentially in the Labrador Sea and the waters surrounding Greenland, exactly the regions where deep water formation drives the amok. Local salinity anomalies in these regions can be significantly larger than the basin averaged Chang-E, and the local anomalies are what matter for the density of the water available for sinking. The trajectory of Greenland mass loss under continued warming is toward acceleration. The Greenland ice sheet has a threshold of its own, a warming level above which the surface melt rate exceeds the snowfall accumulation rate permanently, committing the ice sheet to eventual complete loss on multi-millennial timescales. Most assessments place this threshold at somewhere between 1.5 and 2 degrees Celsius of global mean warming above pre-industrial levels, a range that the current trajectory of emissions is approaching within this century. Once the Greenland ice sheet begins its irreversible retreat, the freshwater flux into the North Atlantic will continue and likely accelerate for centuries to millennia, regardless of subsequent emissions choices. This geological timescale commitment means that even if global emissions were reduced to zero tomorrow, the Greenland melt that has already been initiated by the warming of the past century will continue to add freshwater to the North Atlantic for decades. The amok forcing from Greenland melt has inertia that the climate system has already locked in. The picture is not entirely one of locked-in inevitability. The decisions made in the next 1 to 3 decades about global greenhouse gas emissions will determine the trajectory of Greenland mass loss, the cumulative freshwater forcing on the amok, and, if the amok has a tipping point, whether the forcing exceeds that threshold. Under low emissions scenarios, aggressive mitigation consistent with limiting global warming to approximately 1.5 degrees Celsius above pre-industrial levels. Models project that the amok continues to weaken through the mid-21st century as Warman G. already committed works through the climate system, but that the weakening stabilizes in the second half of the century as emissions reduction takes effect and the rate of Greenland mass loss slows. In these scenarios, the amok does not recover to pre-industrial strength. The warming already locked in produces a persistently weaker circulation, but the total weakening is limited. The early warning signal dynamics do not produce collapse, and the regional consequences, while significant, are manageable. Under high emissions scenarios, a continuation of current trends without major policy changes. Models project continued and accelerating EMOC weakening through the 21st century, with the comprehensive models showing weakening of 30 to 50% of current strength by 2100, and the simplified bistability models suggesting possible collapse within this century. The difference between these scenarios, in terms of cumulative Greenland mass loss, is measured in trillions of tons of ice, directly translating to trillions of tons of freshwater added to the North Atlantic, directly affecting the salinity of the Sinkin G regions, directly determining the forcing applied to the EMOC stability landscape. The choice between these scenarios is not a scientific question. It is a policy question, an economic question, a political question. But the physical constraints are clear. The faster and further global temperatures rise, the more Greenland melts, the more freshwater enters the North Atlantic, and the closer the EMOC is pushed toward whatever its tipping point is. The uncertainty about where the tipping point is does not reduce the relevance of this relationship. It makes the stakes of each increment of a d-ditional forcing higher, not lower. Here is what makes the EMOC story more consequential than the already serious regional climate impacts might suggest. The EMOC is not an isolated component of the climate system. It is connected to, and influences, the behavior of several other potential tipping elements in the Earth system. And the connections mean that an EMOC weakening or collapse could trigger changes in other systems, potentially setting off a cascade of tipping points that is qualitatively more severe than any individual tipping point alone. In 2018, a paper by Will Steffen and colleagues at the Stockholm Resilience Center introduced the concept of tipping cascades, the possibility that multiple Earth system tipping elements, each individually capable of producing significant climate change, are interconnected in ways that allow one tipping point to trigger others, potentially producing a pathway of self-reinforcing Earth system change that carries the planet toward a dramatically warmer and less habitable state. The EMOC is one of the key nodes in the tipping cascade network. Its connections to other tipping elements are specific and physical. The EMOC transports heat into the Arctic. A weaker EMOC delivers less heat to the Arctic Ocean, which could allow sea ice to expand in the Nordic Seas and Barents Sea, a cooling feedback in those regions. But a weaker EMOC also means less heat removal from the subtropical Atlantic, which warms the surface waters of the tropical and subtropical Atlantic. Warmer, subtropical Atlantic waters increase evaporation and atmospheric moisture, intensifying rainfall in the Amazon basin, with uncertain but potential significant effects on the Amazon rainforest, which is itself a potential tipping element facing deforestation-driven drought stress. The EMOC influence on the Sahel rainfall connects it to vegetation dynamics in the semi-arid belt south of the Sahara. A weaker EMOC, by reducing Sahel rainfall, could push the Sahel vegetation toward a different equilibrium, a less vegetated state that reflects more sunlight, cools the surface, and reduces evapotranspiration in a way that further reduces rainfall through a vegetation-rainfall feedback. The West African monsoon has been identified as a potential bistable system with its own tipping point, and EMOC weakening is one of the forcings that could push it toward its unstable threshold. The EMOC connection to Antarctic ice sheet dynamics is less direct, but potentially significant. The deep water formed in the North Atlantic eventually circulates to the Southern Ocean as part of the global thermohaline circulation, Changes in North Atlantic deep water formation alter the circulation patterns in the Southern Ocean, affecting the upwelling of warm deep water that is currently driving basal melting of the Antarctic ice shelves. How AMOC weakening affects Antarctic ice sheet stability is a subject of active research, with results that vary significantly across models. The concept of tipping cascades does not imply that crossing one tipping point automatically triggers all the others. The connections are real, but their thresholds and timescales are uncertain. What tipping cascade analysis implies is that the probability of experiencing severe, widespread Earth system change is higher, potentially much higher, than the probability of any individual tipping point crossing alone, because of the connections between elements, and the AMOC, sitting at a node where it connects to the Arctic, to the West African monsoon, to the Amazon, and to the broader thermohaline circulation that links both hemispheres, is one of the more central nodes in this network. The AMOC weakening that is currently documented and ongoing is not just a story about Western European climate. It is a story about one of the key stabilizing elements of the Earth's climate system losing strength. An element whose weakening propagates rough the system in ways that affect multiple regions, multiple populations, and potentially multiple other tipping elements. Let that sit for a moment. The current is slowing. The freshwater forcing driving the slowdown is accelerating. The window in which the forcing trajectory can be substantially altered by human choices is measured in decades. And the consequences of the trajectory continuing unchanged, uncertain, in their precise timing and magnitude, but bounded on the upper end by historical precedents of a severity that reorganized the climate of the entire northern hemisphere in decades, are playing out in the data that oceanographers are collecting right now, from instruments moored in the deep North Atlantic, recording the state of the system that civilization was built around. The instruments will keep recording. The question is what the data will show. But the AMOC is only one of 9 major tipping elements that Earth system scientists have identified as capable of producing abrupt, self-reinforcing, and effectively irreversible changes in the Earth's climate. The Amazon rainforest, the West Antarctic ice sheet, the boreal permafrost, the Indian summer monsoon, each of them has a threshold. Each of them is being pushed by current forcing, and each of them is connected to the others in ways that mean crossing any one threshold raises the probability of sea-rossing others. The story of the tipping cascade, of how multiple Earth system components could interact to produce a pathway of change that no single model has fully captured, is where this investigation goes next. Tonight, we didn't follow a model prediction. We followed the data from instruments moored in the deep North Atlantic, recording the state of the ocean current that has kept Western Europe's climate mild for 12,000 years. We traced the physical mechanism by which freshwater from the melting Greenland ice sheet disrupts the density-driven sinking that powers the circulation, and we understood why this mechanism has a mathematical structure that permits tipping, rapid, self-reinforcing, effectively irreversible transition to a collapsed state. We examined the historical precedent of the Younger Dryas and understood that the tipping point of AMOC is not a theoretical construct, but a physical reality that has been crossed before in the geological record, under freshwater forcing comparable in character to what is currently increasing. We sat with the genuine scientific uncertainty about whether a tipping point will be crossed this century. Uncertainty that reflects real disagreement among credentialed researchers using legitimate methods, not confusion about the basic physical mechanics. And we understood why that uncertainty is not a reason for complacency, but rather reflects the specific challenge of the most consequential class of climate risk. large, potentially irreversible, and uncertain. Enough in timing that waiting for certainty risks waiting past the point at which the choice remains available. The current is slowing. The forcing is increasing. The window for altering the trajectory is open. Its width is uncertain, and its existence is not. 3 questions that the current science cannot answer with confidence. The first: does the AMOC have a tipping point within the range of anthropogenic freshwater forcing that is plausible this century? The theoretical mechanism exists. The paleoclimate precedent exists. The observational evidence of current weakening is robust. Whether the current forcing trajectory will reach the tipping threshold before the trajectory is altered by emissions reduction or natural variability, whether the ball will reach the hilltop, is a question the current models and observations cannot answer with the precision that risk management would require. The second: are the early warning signals detected by Bowers and colleagues genuine indicators of tipping point proximity, or reflections of natural variability or systematic biases in the proxy records? Resolving this question requires either additional observational records that provide cleaner separation of forced trends from natural variability, or better theoretical understanding of how the AMOC bistability structure produces early warning signatures, or both. Neither is immediately available. The third: how do the connections between the AMOC and other tipping elements in the Earth system affect the probability and consequences of AMOC weakening? The tipping cascade framework is theoretically motivated, but empirically poorly constrained. The thresholds and timescales of the connections between the AMOC and the Amazon, the West African monsoon, the Antarctic ice sheet, and other elements are uncertain. Enough that the cascade probability cannot be quantitatively estimated with current tools. These 3 questions have answers that research programs currently underway: improved ocean monitoring, paleoclimate proxy development, higher resolution Earth system modeling, will progressively constrain. The answers will not come all at once. They will come as the scientific community continues to measure, to model, and to argue about the most consequential physical system that human civilization has inadvertently begun to perturb. What the AMOC story teaches begins with the specific lesson about the geography of climate risk. The AMOC potential collapse is not a global average phenomenon. It is a regionally concentrated, asymmetrically distributed risk that falls most heavily on populations in Western Europe, the Eastern United States, the Sahel, and South Asia. Regions that did not contribute equally to the greenhouse gas emissions that are driving the freshwater forcing that is weakening the circulation. The geography of climate risk is systematically misaligned with the geography of historical emissions responsibility. This misalignment is not a coincidence. It reflects the physics of how the climate system distributes the consequences of global forcing, and it is one of the central ethical dimensions of the climate problem. The second lesson is about the specific danger of irreversibility in risk management. Most risks that humans manage are recoverable. Bad outcomes can be corrected, systems can be restored, mistakes can be learned from. The AMOC tipping point, if it exists and is crossed, does not have this property. A collapsed AMOC would remain collapsed for centuries to millennia, regardless of subsequent emissions choices. The relevant timescale for recovery, the timescale over which the North Atlantic would need to rebuild its salinity gradient sufficiently for deep water formation to resume, is far longer than any human planning horizon. This irreversibility fundamentally changes the risk calculus. The cost of failing to prevent the transition is not the cost of fixing the problem afterward, because the problem cannot be fixed on any timescale relevant to human civilization. The third lesson is about the relationship between scientific uncertainty and policy urgency. The range of scientific opinion on EMOC collapse probability spans from unlikely this century to possible within decades. This range is often communicated as "scientists disagree," a framing that in many contexts implies the risk is not serious. In the context of irreversible tipping points, uncertainty about probability has the opposite implication. When the outcome is irreversible and the uncertainty is large E, the option value of preventing the outcome is highest. Waiting for certainty before acting is most dangerous, precisely when the outcome in question cannot be reversed once it occurs. The fourth lesson is about the connected nature of Earth system risks. The EMOC story cannot be told as a standalone. It connects physically to the Amazon, the Sahel, the Arctic sea ice, the thermohaline circulation's role in Antarctic ice sheet dynamics. The climate system is not a collection of independent risks that can be assessed and managed separately. It is a coupled system in which interventions in one component propagate through connections to others. Risk assessments that treat tipping elements as independent underestimate the probability of severe outcomes, precisely because the connections between elements are the mechanism by which individual tipping points become system-level transitions. And the fifth lesson, the one that the EMOC story points toward with the specific clarity of a physical system whose behavior is documented in real-time instrument data, is about the relationship between geological timescales and human timescales, and WH added means to make choices on one while living on the other. The EMOC has operated in roughly its current configuration for approximately 10,000 years, the entire span of organized human civilization. The choices made in the next several decades will determine whether it continues to operate in that configuration, or whether the freshwater forcing from ice sheet melt crosses the threshold that sends it to a different configuration. The people making those choices will not live to see the full consequences either way, but the consequences will be experienced in the specific climates of the specific places where people live and farm and build for thousands of years. That is the specific responsibility that geological timescales impose on the choices of a single generation. What does it mean to make decisions about a physical system whose tipping point location is uncertain, whose consequences of crossing would be irreversible on civilizational timescales, and whose forcing is being determined by choices being made right now in the energy and land use systems of the global economy? How should we weigh scientific uncertainty about tipping point probability against the irreversibility of the outcome? And does the standard precautionary principle, developed for risks with smaller and shorter-term consequences, apply appropriately to ERTH system tipping points? The EMOC has been giving Western Europe its mild climate for 12,000 years, since the end of the last ice age, throughout the entirety of recorded human history. What does it mean that the generation alive today is the first one whose collective choices could alter that 12,000-year stability? And what responsibility does that fact carry? And what does the history of the Younger Dryas, the documented paleoclimate event in which EMOC collapse produced 10 to 15 degrees of regional cooling in decades, tell us about the concrete meaning of tipping point in the context of human society-wise and their capacity to adapt? If this story stayed with you, if the image of 17 million cubic meters of water per second slowing in the dark of the North Atlantic, or the Younger Dryas precedent of a 10-degree cooling in decades, or the specific structure of a risk that is irreversible once it crosses a threshold kept turning in your mind, tell me in the comments which part of this landed hardest: the mechanism, the regional consequences, the tipping cascade connections. The specific challenge of making choices about irreversible risks under genuine uncertainty. And if you want more stories told this way, following the physical evidence, staying in the science, representing the uncertainty honestly rather than collapsing it into false clarity in either direction, subscribe to Galaxy Pulse. Every video here is built on what the data and the models actually show. The full picture, every time. I'll see you in the next one. The North Atlantic is being measured, right now, by instruments moored 2 kilometers below the surface, recording the flow rate of a current that took 12,000 years to build the climate that civilization was built on top of. The measurements show a current that is slower than at any point in recorded history. The forcing driving the slowdown is accelerating. The window for altering the trajectory is open. We know the mechanism, we know the history, we know the consequences. What we do not know, what the instruments will tell us, year by year, as the data accumulates, is which side of the threshold we are on. That is the question the ocean is answering in real time. Whether we are listening carefully enough is the question we are answering. Galaxy Pulse, beyond the headlines, every single time.